All right, here we are. This is going to be part 3 of the screencasts to help physics students review for midterms. And we're going to go back to this question we ended with in the previous screencast, because our discussion kind of got out of hand. And let's talk about what students should think about when you see this question. And like most of these questions, well, all of these questions, you're going to get a choice of multiple, you're going to get a selection of multiple choice answers. And you've been taking my class long enough to know that the last one is likely to be something like none, or more than one, or not enough information to tell. So read carefully and be prepared. One thing I can tell you about the midterm, all the multiple choice questions have only 5 answers, 5 choices this time. Yes, there is a raw chance of 20%, but in fact every question has at least one answer, which is obvious and very tempting and completely wrong. So if most people just, if a naive individual makes their best estimate at each of these questions, they'll probably get less than 20%. Because this is a chance for you and me to see how much you learn.
To assess your knowledge.
Or better yet, I would say to assess your new skills. But anyway, so what statement is true of every object that has mass? What might be up there? Let's see. What might be not true? Let's list some things that are not true. Let's list some things that might be true. Talk to yourself, talk to each other for a minute, and see if you can come up with 1 or 2 things that might be in the true statements about objects with mass and the not true. I'll put some easy ones up.
Face the corner. Face the corner.
Hi.
Watch your eyes. Look right at me. Corner. Hey, look at me. Look at me. Look at me. Look at me.
Just remember that if you're in social conversation, that will be captured on YouTube too.
Oh yeah.
Let's see. What else is obviously true about something with mass? Joe, over here at this table, please, with your notebook in front of you. I want you to sit there next to Amanda.
It's going on YouTube. Joe.
Yep. Okay, Ian, come to the black table. No more interjections, please. Thank you very much. I know that this is a piece of cake for you, but you got to be prepared to help out your classmates. And because of your confidence with this, you are in particular danger of falling for those tempting answers that look obviously correct and are not. Black table.
You should just make it harder.
Anything else true about mass? It's made of matter, whatever that is. An object that has mass participates in gravitational interactions. What's that mean?
That it's always gravitational.
Yes, totally. If there's an object and it's near a planet such as our Earth, the Earth is going to pull on it. There might be 2 ways to answer this question. Do things other than the Earth pull on objects by gravitational interaction? Well, in our daily life, it's only the Earth that we notice. Kinda. Does the moon pull on things with gravitational forces? Yeah. Sun? Yeah. Where does it stop? What does and what doesn't pull on other things with gravitational interactions?
I think that like everything does, but just when it's small, it's not significant.
Absolutely right, Isabella. Yep. Every bit of matter participates in this gravitational interaction. And even the smallest chunk of matter has a gravitational field and will attract other chunks of matter. How come we don't notice it in our daily lives? Because it takes a tremendous amount of matter to make a force big enough for human senses to notice. Okay? Consider the calculator on the desk here. The entire Earth is pulling on that calculator, but I can balance that pull of the Earth with barely detectable effort. Now let's see. Let's use one of our other lessons. If the Earth is pulling down on this object, name another force you know must exist.
The force of
Ian?
the force of whatever is pulling or pushing up on it.
Oh, okay. Yes, that's a really good point. If this is not, there may be something balancing the force of the Earth. Yep, same thing Liz said. But if I say force of A on B to you, what do you think of? Yes. What's that mean? Force of B on A means what? Yes. Remember your Newton's third. For every force of A on B, there's an equal and opposite force of B on A. So if you hear about force of Earth on object, you think
Wait, what? Force of Earth on object?
yeah,
I think force of object on Earth.
absolutely. If there is a force of Earth on the object, and it's, say, this direction, then there must be a force of the object on the Earth equal and opposite in the up direction. If we drop an encyclopedia to the floor, how come we don't see the Earth accelerate upward like we see the encyclopedia accelerate downward?
Because the force of Earth is bigger.
You got it in your brain, use the right word.
The force of Earth is more pulled than encyclopedia pushing up.
Which is greater, force of Earth on encyclopedia or force of encyclopedia on Earth?
Force of Earth on encyclopedia.
That's really easy to think. Is.
They're equal, but the Earth is a greater mass.
Right? So that's exactly what's supposed to happen. Like, although the force of the object on the Earth is the same as the force of the Earth on the object, the encyclopedia accelerates because it has a very small mass. That same force hardly makes the Earth accelerate at all. So, who knows what you'll see here, but you may have to use anything you've learned so far. Let's see. What might be offered there to try to trick you? Not true of objects with mass. Let's see, where would you put this statement? Let's do again. Let's do for true and for not true. Here's a statement. An object with mass always moves in the direction of the total force exerted on it by other objects. True column or false column?
False.
Good. What's your counter example?
False.
Here's how you survive when you have 4 statements or 5 statements and you have to judge the truth of each one. You mark up that paper and try to decide whether each answer is true or false. Now, do you look for reasons to believe it's true? No. Excellent. Because that's not what scientists do. All you need is one thing that shows it's false, and you know it's false. So, anything you see, think, how can I prove to myself that that's not true? So what's an example of an object moving in one direction, even though the total force exerted on it is not in that direction?
Flipping the coin in the air.
At what point? Okay. Yep.
One at the highest point.
Let's see.
Because the direction, no, it's going on its way up.
Excellent.
Because
Excellent.
way down, the direction of force is pushing, it's forcing it to go down. You told about force, but it's still on its way up.
Absolutely. So what's the effect of the downward force, although it's moving up?
It's slowing it down.
Yeah, awesome. Okay. So an excellent counterexample, something thrown up. It's moving in this direction. Its velocity is up, but the total force on it is down. That's why it's accelerating in the down direction, and the speed decreases. Speed decreases, stops, then the speed starts increasing again in the down direction. So this is not true, and this goes in the false category. Careful for things like this. I know 500 different ways to see if you really changed your brain to include Newton's first law. All right, next slide. Oh, Tara says that an object always moves in the direction of the total force exerted on it by other objects. If you push a cart on a level, frictionless track so that it rolls faster and faster, and then stop pushing, which of these statements describes a prediction made by Tara's idea? Now, here's a suggestion. The time that you might be tempted to spend staring and thinking hard about this, use it to make a sketch instead. Doesn't matter if it's a good sketch or a bad sketch, so they'll get better over time. Make a sketch right now to help you organize and interact with this information in your mind. Cart, frictionless track, push. It's going faster and faster. And then at some point, you stop pushing, and something else is going to happen. Okay. Careful.
It's the force of the hand is going to go away, so if I will go down, but the cart's not going to stop moving because of friction.
Let's read the question again after you made your sketch. Some things are underlined here. That must be important. Tara says an object always moves in the direction of the total force exerted on it by other objects. What is moves in the direction? Yeah. Is it velocity, acceleration, something else? Okay, speed. Yeah, this is speed with direction is velocity. So Tara is saying the velocity, Tara says that the direction of the velocity, let's use our funky notation because space is limited, the direction of the velocity is the same as the direction of the total force. That's her idea. Now, which of these statements describes a prediction made by Tara's idea? Another underline part. And you know that we don't abuse underlines. So talk with each other. I want not your prediction, but Tara's idea's prediction about what happens after you stop pushing. Talk to each other, make a force diagram. If you're watching at home, make a force diagram for this part, pushing, and this part, stopped pushing.
Isn't it only recording your voice though?
Yep, and what I write on the board.
Because otherwise, like, the thing with the getting smaller and don't take your trees that way.
I'm going to draw the, I'm going to start the force diagrams. Vertical forces are balanced, so we can ignore those. There is a force of hand on cart. So for pushing, we see that the total force goes in this direction. Tara says see, my idea works, because the cart is moving in the direction of the total force on it. So here's a, let's see, here's an answer that may appear. Is that a prediction made by Tara's idea?
No.
Yeah. Well, not my idea. No.
By Tara's idea. No, because Tara's idea says,
That won't stop. It'll just keep going in a straight line.
well, which?
It won't stop. The cart will always keep going at the same speed.
Is that what Tara's idea says? First of all, okay, let's go back to our force diagram. What is the...
move in the same direction. It doesn't say that.
Well, let's find out what's the total force on the cart after you stop pushing.
0.
Right, because there's no longer any hand, and those vertical forces of earth and surface are balanced, so the total force exerted on the cart after you stop pushing is 0. So Tara's idea says that what should happen? Yes. Tara's idea says no force, no total force, no velocity. It ought to stop. Right? And we know that's wrong. That's not what happens. So this would not be an answer to the question, because this is not a prediction made by Tara's idea. And this is how we work as scientists. We don't test. a prediction is not what you, the scientist, thinks is going to happen. A prediction is made by the idea you are testing. An idea, a single idea like this, can produce many different predictions. Some may even come true. But as scientists, we don't keep any ideas unless they make predictions that always come true. Because science is about reliable conclusions. So if this idea produces a prediction, if this comes true and this comes true, that's great. But if there's even one experiment that does not come true, this idea is no good to us. Dig? Read carefully. Sketch your fingers off. Look how much easier it is to reason about this question because of a little writing and sketching. Carrying on. Which of the following describes a Newton's third law force pair? Well, let's see. You'll even have this on a formula sheet. But we remember that the force of A on B, if there is a force of A on B, there's a force of B on A of equal strength in the opposite direction. So it can't hurt to remind ourselves of that. What kind of choices might we get for our A, B, C, D? E. Let's see. What if it's in the form of is that a Newton's third law force pair?
No.
Mike pulls on Joe, 10 newtons north. Liz pulls on Madison, 10 newtons south. Those are equal and opposite forces, but they're not a Newton's third law force pair. What if it's x on y, which is equal and opposite to z on y? Nope. Doesn't matter if they're equal and opposite.
It has to be x on y and y on x.
Yep.
Otherwise, x has to be negative.
And they're in, yep. Yep, good. At the same time, right?
Yeah. The y on x will be negative.
Good. Hey, when in doubt, sketch it. Let's see. Peter pulls on a string, which pulls on a toy. Peter, string. It's hard to get things. Here's, let's see, Peter on string, string on toy, Peter, string, toy, force of Peter on string. Wait a minute, so that would be, the string would be the object. Here's the force of Peter, force of string on toy. Hang on, that's another force diagram. One object per, okay. This is not Newton's third law. Two different, Peter is pulling on two different objects. Remember, stop me if you got a question or what have you. Carrying on. Which of the following does not describe a physical quantity? Okay. What kind of thing does describe, oops, a physical quantity? Here's the definition. A physical quantity is something about the physical world, the real world, which you can measure. As distinguished from, okay, this is not the same as a unit of measurement a physical quantity might be something like the length of this line is a physical quantity as it appears on the screen. Here to here. That is something about the real world which you could measure. You could express the same physical quantity using different units of measurement. Let's see, 45 centimeters or 27 inches. So, inch, centimeter, meter, etc. could be used to express the physical quantity, the length of that line. It's not only things you can touch and poke at that you can measure, though. If you are measuring a physical quantity like velocity, sure, you need a stopwatch or some way of measuring time and measuring position. But this is made out of the combined physical quantities. Well, change in position, which is a physical quantity, over change in time, which is another physical quantity. And that is a legit physical quantity. Likewise, force, momentum, mass, etc. Ideas about what might be given to try to trick you? Is right, this is in the easy category. All right, which statement does not describe part of the scientific reasoning process? We've been talking this period a lot about what scientists do. Take a minute at your table with your pals or at home. Yes, that's right. I like this. I like this. At home, you at home. Pay attention. Write down a couple things that a scientist does not do when she's trying to think about something or figure something out. Write it down at home. Don't just think about it. Go ahead, I'll wait. Yes, Mike. Cool. Does a scientist estimate?
No, it's not exact.
in the zombie problem, didn't we estimate a zombie mass and velocity? Right?
Yeah.
And we did. Then that did get us some reliable conclusions. So, good thinking. Let's make not used and is okay for science if as part of this balanced breakfast. So estimating is okay. Show me a hand.
Hello.
Okay. What should I put up here?
I thought you just wanted me to show you the hand.
Make it easier. Just give me something. I'll put it up. You don't even have to tell me what column it goes in.
Hypotheses.
Harvard.
A hypothesis. What does she do or not do with a hypothesis?
They use to figure out what the question is or what they're trying to solve.
Okay, she thinks about what she's trying to solve. Yep. A hypothesis. You've heard lots of definitions of hypothesis. I like Buddy the T-Rex's definition. It's an idea about the physical world you can test. Okay. So I guess one thing is a scientist isn't going to call it a hypothesis unless it's something she can test. I leave it as an exercise to you. Can you think of any ideas that can't be tested? You can Google the flying spaghetti monster if you want some examples of ideas that cannot be tested. Something else a scientist does not do.
Does not do?
Yep. Or does, whatever.
He doesn't not rule out things.
Doesn't not rule out things.
Yes. Meaning in other words, he does rule out things.
Rules out things. I like that. Okay. A scientist rules things out.
Discards ideas proved false.
All right. You know what? That's great. Yeah, that is the heart of science. If you haven't been able to, you believe it only to the extent that you haven't been able to rule it out. Okay, so therefore, what's something a scientist would ever do? Perhaps.
Believe that flying spaghetti monster exists.
If the hypothesis of the flying spaghetti monster cannot be tested, the scientist won't say that's not true. The scientist will say, I can't tell you anything about that.
If it can't be tested, then is it not a hypothesis?
If it cannot be tested, it is not a hypothesis.
Okay.
And science says, not my job. I can only tell you about ideas that can be tested. If you want to say that the flying spaghetti monster manipulates my observations with invisible noodly tentacles that I cannot detect, I can't test that. So I can't tell you whether it's true or false. That's not my business as a scientist. Now let's see. Let's throw some things out that people do when they're reasoning non-scientifically. Let's see. Does a scientist make assumptions? Like, I'll assume that the force of friction is small enough to ignore. Is that something a scientist does? Yes. But she'll say it. She'll mention that. She'll say, well, the following conclusions are based on the assumption that friction was small enough to ignore. Throw me something else. Here's one way of representing in a simplified manner what a scientist does. He or she watches the world. That's fun for scientists. And what's fun is when you watch close enough to form a, well, you see something interesting. Yeah, well, yeah, I suppose. But you might get ideas about the world. Wow, does that always happen?
Yeah.
When the scientist gets an idea, he or she will test that idea. And then maybe we discard the idea. Maybe we improve the idea. Or maybe we use the idea to make new ideas. And the more ideas we have, the more we can observe. The more we observe, the more new ideas we get. This is fun for us. The world is more fun when you're part of it, when you're interacting with it. This makes you more interested. So anybody got anything to put in the not used by scientists category?
No.
Does a scientist look for proof?
Yes.
No, no, no.
Evidence.
No, it's a contradict, which is a
Yes.
thing to intro.
Remember day one, 10 TVs.
Oh yeah.
Okay? Remember 10 TVs. And what do you do if you think your teacher's a TV thief?
Look for receipts.
That's right. You do check receipts. You don't look for a ski mask. Because there could be any amount of reasons to believe that he is a TV thief. But the only definite conclusion is, no, there's receipts, he paid for them. All right, end of part 3. This and the remaining parts will be up on mophysics.com.